gonna use a grapher to see few examples of what the graph of a function of two variables look like. We've seen a couple of examples of graph of functions of a single variable. So you will see like a curve or a line on a two-dimensional space. So if I have a function with two variables, so what does that mean? So I will have, for example, a of xy equals x plus y plus 2, for example, like that, right? So now I have two input variables, and given a relation, which is the function a of xy, I would have an associated output value. And as you can see here, what I get is a plane, right? Which makes sense because it's degree 1. Okay, so if I now play with this a little bit, if I do x squared plus y plus 2, and let's see what it will look like. Ooh, looks like this. Okay, kind of like a parabola, but it's two-dimensional. It's in three-dimensional space. So this is more like a paraboloid. Okay, so I can make it simpler, erase the y part. Okay, so that just means for any value y, I would have exactly the same output value, which is defined as x squared. So the x variable controls the height, the a of xy, but for the y variable, it doesn't really make a difference. Okay, so I can have a function of two variables defined only involving one variable, for example, this. Okay, just like when we have a function of one variable or two variables, we can have it as a constant function. So now you see, for any xy value, the output value is always 1. So in R3, what we see is a plane with a equal to 1 all the way. All right? Okay, so now you get the idea. If I say I have a function of 3 variables, what does that look like? Well, then I can't really graph it out for you, because what does that mean? If I have a of x, y, z, I have 3 input variables, then I will need a fourth dimension, a fourth axis to print out the output value, right? But I can draw something that's in 4-dimensional space for you, so you're gonna have to use your imagination to think that if I'm seeing a function of 3 variables, the graph is gonna be something that's sitting in a 4-dimensional space, like R4, if you will. Okay, so I'm gonna show you a few examples. So here we have a constant function. Constant function gives us a like horizontal plane, as you can see over here. Okay, if I tilt it a little bit, that's what you get. If I have a function defined linearly, meaning both the degree of x and y is 1, then I get a plane. So this sort of function is called linear function. Okay, you see this example already. And if I have x squared plus y squared, oh, here we go. You see, this is called paraboloid. Okay, and the scale doesn't have to be the same. So I can have 2x squared plus 3y squared. You can see it's still like similar shape. And I can do, let's say, like -1. What this does is to shift the parabola down by 1 unit. Okay. and I can have, let's say, x squared minus y squared. What's this? Ooh, this is hyperboloid. Okay, so if you look at the cross section, looks like a hyperbola, but that's what the surface in R3 looks like. Okay, then of course I can change the coefficient, have like 2x squared minus, let's say, I get dizzy, how come it doesn't stop rotating? Minus, let's say, 5y squared a. You see, it's still like same shape, but scaled differently. Okay, so if we have like x squared minus y squared, this type of function, it gives you a hyperboloid. All right. Okay. Now let's look at another one. Square root of x squared plus y squared. Guess what you get? Ha! You get a cone. Like that. Like an ice cream cone you have. Okay? And let's play with the coefficient a little bit, just so then we know what's happening. So let's put 3 here. Oh, this is what I have. You see, it's still like cone, but if you look at the cross section, this is more. This is like ellipse as opposed to a perfect disc or circle. Depends on how you say it. Okay. If I do like minus sign, oh, this is what you see. You take the square root of a hyperboloid. Okay. All right. So now you have seen several standard examples of a function of 2 variables would look like. So again, if it's a function of 3 variables, then it's gonna be something sitting in R3. Sorry, R4. Okay. If it's a function of 4 variables, what space would the graph be sitting in? It would be in R5, a 5-dimensional space, because you need 4 axes, 4 dimensions to take the input x, y, z, w, like the 4 variables. Then you have to have another dimension, which is the 5th dimension, to print out the output variable, right? Okay, so now you have the idea, and the calculus is gonna get interesting.